Hello, everyone. Welcome. You're out there. The plan for today is I want to first just make sure that the stuff that we talked about at the end of class last time, central limit theorem, whether that's clear. I just want to go through the last example that we didn't get to on that sheet. Go through some basics with RStudio that you guys practice ahead of time just to make sure that RStudio is working for you. And then we can talk about the exam. So if you're someplace where your camera is easily turned on, it'd be great to see you. If not, that's okay. I'll look at your black box, but it is quite nice to look at somebody as opposed to looking at that. Okay, well, nice to see you, David. Cool, all right. It's so exciting. I see nobody, so it's great to see you too, Derek. Great. Thank you, everybody. Cool, okay. So last time we were working with central limit theorem and trying to kind of motivate where that result comes from and how to use it. So keep in mind this central limit theorem, we use this when we're trying to calculate the distribution of sample statistics. So the idea is you have some population X and it's large. So there's a lot of data in here. But from that, you could calculate the mean and the standard deviation of that data. Okay, and in fact here, the shape of this data doesn't need to be normal. It could be any shape data. So maybe it looks like this. So then we pick a random sample. Then we pick a random sample size n over and over again for each sample. We compute the mean. So remember, we use this x bar to denote sample mean. And then we can look at the distribution of all sample statistics. So this we would call the distribution of the sample means. So we denote that with an x bar. And so what the central limit theorem tells us is, first of all, it's going to be normal. Okay, and that's going to be the case even if the population is not normal. So that gives us this piece there. We observed that the mean of this sampling distribution, in other words, the expected value of the sample mean, is going to equal the population mean. We would expect our samples to have a mean similar to the population. So we can put the center of that normal distribution is going to be at the population mean. And then the last observation is probably the trickiest one, which is if we want to describe the standard deviation of the sampling distribution, remember we call that the standard error. And this is much less than the standard deviation of the population. So we need to scale this down by a factor of square root of n, our sample size. So the central limit theorem gives us a way of theoretically describing the distribution of sample means. So that's a quick recap of last class. Any questions? Okay, and so we did one at the end of class dealing with BMI, and so I just want to go through a second one. The solutions are up online just to make sure you're clear about that. They're the very last problem on your homework assignment which is not going to be collected, but which is up there for practice for the exam, has one like this. So it would be good to make sure that you can practice one of those before the exam. But questions? Okay, now I believe you because I can see that you all are very focused and don't have the I have a question face. This is great. Okay, so for question 7, the idea here is let's say that there's some standardized test, and what they know is that out of all seniors that take this in a state, the mean score on this achievement test is 60. The variance, so the standard deviation squared, is 64. So we want to think about, okay, some school is claiming that they're performing up to average, up to the state average. And so they pick a random sample of 100 students from their school. And those 100 students have a mean of 58, which is a little bit less than the average. So it seems like these are pretty close. So the question is, like, how likely is it if a school is performing up to its average? So if they're claiming they're on average with the state, that they would have an average which is just like 2 points lower than the average. So what we're trying to get here is, what is the probability that a certain mean for a certain sample size is less than 58? So this is not asking like how likely is it that one individual student got below a 58. So that's why we need to use a sampling distribution. So anytime that we're asked questions like, tell me something about the probability of getting a mean which has a certain value, that means we want to use sampling distribution. So what we need to do is describe this distribution. So we know that it's normal. We need to identify where it's centered, what the standard error is. And the key part of this process really is making sure that you adjust the standard error. So in this case, let's just be clear about how we're using the notation. So this is really important that you get comfortable with this. It'll be a lot easier for you to explain your work to others. So the population mean, right, that is what we've been using. This is the mu with a x referring to the mean of random variable x is 60, and the population variance is 64. So there we go. Okay, so if we're then trying to describe x bar, right, the fact is we should expect the sample mean to be the same as the population mean. So we're going to put 60 in place over here. And then in order to find the standard error, right, that means what we need to do is first take the standard deviation of the population. So we take the square root of the 64. So that's where this 8 comes from. So we take this standard deviation of the population and then divide it by the square root of the sample size. So since the population variance is 8, right, the population standard deviation is 8, and then we divide that by the square root of 100, which in this case would be 10, and that's where the 0.8 comes from. So the big change here is the standard error, whoops, is 0.8. compared to the standard deviation of the population, which is 8. Okay, so again, you should expect that the standard error gets smaller and smaller and smaller as the population gets larger and larger and larger. And the standard error, in case you're wondering what, like in practical terms, is that representing, the standard error is really telling us like how much variability do we have in sample means due to sampling, right? Just due to the fact that sometimes we pick different individuals in different samples. So how much variability should we expect in sample means? And it's less variability than we would expect in the scores of one individual student compared to another individual student. We would expect a bigger variation of individual test scores than collections of like a mean of 100 students together. So really the key here is finding a description for the sampling distribution for the mean, and then calculate this probability. We could just use R to calculate that. So we've got the 58 goes in over here, the mean goes in over here. And now, since we're working with a sampling distribution, just be really careful that I don't put in the 8, which is a population standard deviation, but I scale that down to get the standard error first. And what you can see is you might be surprised that it would be highly unlikely to pick a group of 100 students, those students that have an average of 58. That would give us some evidence, in fact, that the school is not performing like up to average state standards. Any questions about that? So just one kind of last comment about the central limit theorem. Okay, we can think about like what happens to the sampling distribution for the mean as n gets larger, n being the sample size. So as n gets larger and larger and larger, the shape of the sampling distribution for the mean is going to get more normal. The center of the sampling distribution isn't going to change, right? It's still going to be at the population mean. Okay, whereas the standard error does depend on n, right? So the expected value, the center, this is independent of n, whereas this one is not. So that's a good point to make sure that you're clear about. Okay, so we get less variability in sample means when we pick larger and larger population or samples. So for example, these could be good multiple choice true false questions on an exam, for example, about the central limit theorem. Okay, any questions? Okay, so if there aren't any questions, then I just wanted to go over some basics with exploratory data analysis in R. I think most of it you guys probably got going on the quiz. And I don't think this will take too much time for us, just to make sure we've got some things working in our studio. And then we'll have time left to talk about the exam if you have some questions about that. So yeah, go ahead and open up R if you don't already have it open. And trying to see here, I can have R or the worksheet open. Maybe I'll screen share my screen. And so I'm just opening up this worksheet 8A on exploratory data analysis. And let's see what I can do here. This might be confusing if you see yourself. Let's see. So you guys are looking at my desktop. Can you see yourselves in this little picture? Okay, that's good. You don't need to see yourselves. Oh, some people can. Okay, but are you guys able to see my desktop so you can see the worksheet? And if I had R up here, you guys can see R now?
Yeah.
Okay, cool. Okay, so yeah, so just some basics with R in general is right now, right, my R window, I'm in R Studio. Just be aware that, there's R, which is kind of the programming language, and then there's R Studio, which is like the interface that you can use with R. So since we are going to be running code that has many lines of command lines really quickly, it's really important that we're using R Studio and eventually using scripts as opposed to entering individual commands from the command line. But down here is our console where we can do individual commands. And then up here is where we could enter like multiple lines of code that we can execute at once. So hopefully you've all installed that tidyverse and resampledata package. So just so you know, if you've installed those packages, you don't need to do that again. But every time you open up a new session of R, if you want to use those packages, you do need to load them with the library command. So it's just a good habit when we're opening R to just enter this command to make sure that it gets loaded up. So now we're going to have all of the data sets from our textbook in there. And this package tidyverse is probably the more commonly used data analysis commands are in here. So I'm going to load library tidyverse in here as well. When you're uploading these into R, you might get some error messages. For the most part, I would not worry about them. They might look concerning, but I just tend to ignore them and then worry about it if my code's not working. Okay, and so yeah, so we've got these kind of different areas of where things are going to go. So down here is the console, and this is where we can enter like one command at a time, and we can see the output of those commands. Great. So any questions that you guys came across just kind of interfacing with R Studio?
Yeah, when I after I loaded it, so I installed the packages and then you load it with the library function. In order to view the data sets, like
Okay.
I couldn't use view, like lowercase, I had
Yeah,
to do
so for
upper.
example, for those that might have had trouble, sorry, with the view command, so if I want to take a look at the data set that you guys had for the reading assignment, which was book prices, I hit view book prices, and I realized that this view command with the lowercase is actually part of the tidyverse package. So if you had an error, that was my fault. I should have been really clear that you needed to also enter this library tidyverse command. I didn't realize that.
Yeah, it worked with
Keep that in mind.
uppercase. I figured it out.
Have it to just kind of run these commands when every time we open up R, and then we won't have to worry about it. But yeah, so when we view this, you can see that it pops up over here. And if you were worried, like I was running an R script, what happened to all of the code that I had up here? It probably hasn't gone away. You just have different tabs up here that you can move between. So yeah, so this tells us what our data looks like. And so just so it's clear, when you're doing data analysis, we say that data is tidy in the sense that each of these rows should correspond to a different observation, and each column should correspond to a different variable in the data set. Very well, we could have inverted it and done it differently, but this is definitely the default when we're working with data, whether it's in R or Excel or any other data management software, that we really think about each of these rows as a different textbook in this case. So each observation is a different textbook. And then for each textbook, in this case, we have three variables. What subject is that textbook in? What area is that textbook in, which seems slightly more broad than subject, and then how much was the book. So these first two variables we would call qualitative because they're placing things into categories. This last variable we would call numerical or quantitative. And it's worth making these distinctions since the type of analysis that we can do is different if we have categorical data as opposed to numerical data. I can't say what is the mean of the subject, right? Because there's no values there. But I can say, like, what proportion of books were from biology? That would make sense. Whereas for the price, I can ask what is the mean book price for that. Any questions so far?
I was just curious, like, is it help?
A really good general thing to know is that if you ever want to get help documentation for a command, like how does the view command work? I don't know if my desktop is big enough here. I'll zoom it in. If you just type a question mark before the command, then it typically opens up help documentation if there is some. This seems to not have help documentation for it. But if I'm working with barplot, just hit question mark, barplot, and that opens up help documentation for bar plots where you can see there's like all sorts of options that we can use to tweak the output of that command. Okay, yeah, so we've got these packages installed. This was dealing with the flight delay data set that was up in the video. So I think the video pretty much took us through the part where we got a bar graph for that data. But just to kind of go through that process again, if I wanted to get a table and I want to just focus in on like a frequency table for just one of the variables in the flight delay data set, okay, first of all, here's the data set up top. So it's a much bigger data set, like 4,000 entries. You don't want to go through and count things by hand in a data set like this. And so one of these variables was called carrier. And there were two carriers in this data set. UA is United, and there's AA, which is American. So if you wanted to, for example, say, out of these 4,000 flights, how many of them were for each airline? That's what the table command can do. We got flight delays, and then when I want to specify a particular variable in that data set, I do it with a $sign. And that gives us a count of how many flights were done by each airline, for example. If I want to create a plot from this, right, again, the command here is barplot, and I need to input into that this whole table command. And that's what happens in the little box on the right there, right? So there we get our graphics for this. That's pretty lame looking graph, so I would definitely encourage you to play around with the options and get that, you know, if you want it aesthetically looking different, you certainly can move things around. What's really nice in R and any programming language is rather than have to like enter this command every time I want to access this data, is I can store this output to an object. So if you want to save the output to an object as opposed to see it, then in R, this is the symbol that we use to assign output to an object. It's literally that angled bracket, kind of the you know, inequality, and then a minus sign. I think there are keyboard shortcuts if you're on a Mac. If you hold the Option key down and hit the minus key, it brings up that character. I imagine if you're on a PC, it's something pretty similar to that. So if I want to store that output, I would just say, it kind of works a little bit reverse in that you say, here's the thing I want to create, and then here's the output that I want to send to that object. And now, rather than like type out that whole table argument, since I've already saved this to airline, I can just hit barplot airline and it creates the same thing. Any questions? Okay, so that takes us up to this point over here in the worksheet. So for a contingency table, that's like a two-way table, or what we've been calling now a joint distribution. So this is what we use. Sorry, I see there's a chat in here. Sorry, I missed the chats over here. Yeah, okay. So if we want to create a contingency table, first thing to note here, and that I don't have any place to write, but that is, contingency tables are used for categorical data. So it would make sense to look at a contingency table for the flight length in terms of minutes. Contingency tables just work for when we are placing our observations into different categories. So if you think about, we've been doing it like with medical screening, you're either in the test positive or in the test negative category. And then the other side had whether or not you have the disease. So we're only going to be using these contingency tables when we're working with categorical data. And so this question C is asking us to take a look at comparing whether or not a flight was delayed by more than 30 minutes. And so if we look in the data set, that variable is called delayed 30. And that's categorical, right? So you can see that we have some information about how long a flight was delayed. We can either describe that in terms of minutes and make that a quantitative variable, Or we could think about it in terms of categorical data, in terms of was the flight delayed more than 30 minutes? So what we want to say is like, okay, was United or American any more or less likely to have a flight delayed for more than 30 minutes? That might be a question you're interested in. So if we want to create a table for two variables, then we just do that. So over here, what I want to do is create a table for two variables. And let me assign it to a new object here. So I'm going to call this thing delay. I'm going to create a new object called delay. And what delay is going to consist of is this contingency table that's going to input two categorical variables, the two variables I want to compare. So one is flight delays delayed, not 39, delayed 30. And the other is flight delays, and the variable is carrier. So this is going to count up two different things. It's going to create a joint distribution table for these two variables. And if I hit enter, I don't see anything, right? Because rather than print this output, I said, send this output to this object delay. And so if I actually want to see what I just created, for example, I could say print delay. And it'll show me what is inside of that object delay. Okay, so hopefully you're trying this with R as well and getting similar output. And any issues that you guys are having with this? So now, if the question is like, which airline is more likely to have a delay of over 30 minutes? This means delay of over 30 minutes, right? We can see here, American, how we can read this table. American had 339 flights delayed over 30 minutes. Don't worry. It's trying to make sense of that. I don't care. Just trying to write this up someplace where you guys can see it. Okay, whereas United had 204.
Is there a way in R to like make that a string? So it's just like text?
I'm trying to make some sense out of this. So I'm looking at these values. American had 339, delayed over 30 minutes. United 204. Would this tell me that American is more likely to have a delay over 30 minutes compared to United? Maybe not. I can. Can you try? I think you're on mute, Christina.
Can you hear us now?
Yes.
Oh, okay. Yeah, I wasn't sure because a few people asked questions, and yeah, and like yeah, I
don't know if you're. I think I was unmuted. Maybe I don't know if you guys were trying to talk, but I can certainly hear you.
Okay, cool.
That means I can hear anybody else who is interested in talking too. So what do you guys think? Is it what you agree with this statement that I wrote? So here are two statements over here. I'm just getting that from the data, right? I'm not making that part up. That's what R is counting for us. The question is, how can we interpret this So here's one way that I might think about interpreting this. So when I say American, I mean American Airlines is more likely to be delayed over 30 minutes than United.
I think it would be, or it would make more sense to figure out the percentage, like
Yeah.
for airline, so that way it makes more sense with like how many total flights there were.
That's right. That's right. So we don't want to forget that we're sort of comparing apples and oranges here if we just look in terms of like absolute totals. The fact that we're seeing more American Airlines flight delayed than United might be a result of them being more likely to be delayed, or it could just be like there are a lot more American flights in this data set than United. So maybe we're just seeing there's overall more American airline flights. So we might want to compare proportions. That's right. So for example, I could say 339 American flights were delayed out of 2,906. And you can use R as a calculator. R can calculate this for me. That tells me that, about 13% of American airline flights were delayed over 30 minutes. And for United, we could take a look at the 204 delayed out of 1,023. We can see as a proportion, relatively speaking, is that we're seeing there's about 18% for United compared to American Airline, which had 13.5. Okay, I'm not trying to tell R to do things. So when we're comparing frequencies and we're trying to say, is this thing more likely than that thing, keep in mind that we typically would compare proportions and not counts, since we want to take into account that we're picking from two different sized populations. American airline flights was a much larger population in our data set compared to United. Okay, any questions? Yeah, so if I want to take a look at kind of a clustered bar chart, for example, I want to take a look at plotting both of these variables together, then I've already created this table that's called delay. So let me just see what happens if I just do barplot delay. And you can see over here that created what's called a stacked bar chart. And we don't really see much. You can probably see there's probably an axis that we would want, like what's the difference between shading it lighter gray and darker gray. It's not that clear, but you can see what's going on here is we have all of American airline flights. The dark gray is how many of them were not delayed more than 30 minutes. This is telling us how many were delayed for over 30 minutes, and so on. So this is what's called like a stacked bar chart.
Is there an option to normalize the charts?
Yeah, so if you're kind of looking at the spreadsheet or worksheet over here on the left, this has some other options that you can use to try and make it a little bit prettier. So there are definitely tons of things that we can do. So here are a number of options. So I'm just going to execute this code, what happened here. I see. Maybe I want this. Oh, I see. I think I'm missing okay, let's try that. Okay, that kind of did it. Yeah, so sorry, I'm just trying to play around with these options here. What was the question? Sorry, you wanted to do what?
I was just wondering how you would make it normalized so they're on the same scale.
I see. Yeah, so that you're comparing maybe like proportions instead of counts. Yeah. Yeah, we'll get that in a second. That's right. We would want to compare proportions, so we'll think about how we can do like a proportion table. Yeah. Sorry. Yeah. So this command over here, we can just kind of tweak things to add an axes over there. Sometimes it's nice to see them side by side, but again, we are still kind of comparing, you know, things from very different populations. So even though we see that this gray box over here for American is bigger than the gray box is for United, we might be losing the fact that relative to how big the dark gray box is, it's not that big. Okay, maybe I'll hold off on this histogram for a second. But yeah, let's answer this question about what we could do for this proportion table. So for this, if you want to compare proportions instead of counts, then that's what's called prop.table. So you do a proportion.table. And here you would enter in the two variables again. So for example, I could do flight delays. And the first one was delayed 30. And then it was flight delays carrier. What happened here? I see. Sorry, I need to enter a table name here, which was delay. So rather than say table delay, you should put prop table delay, and that creates proportions out of these. The thing that is a little bit confusing is this still isn't doing it quite correctly as we would want. So there's different ways that we can add it up, right? And so if you do some arithmetic and you add up the nose, like you can see that things aren't adding up to 100%. You might want to think like, so right now, all I'm saying is like the fact that we have this is 0.623 is telling us it's 62% of American airline flights were not delayed by that much, by more than 30 minutes. But then if you say, okay, well, 9% of them were delayed by 30 minutes, somehow this isn't adding up to like 100% of American airline flights, right? If we're trying to calculate what's going on. We calculated back here.
It looks like it's summing across the row instead of the column.
That's right. It's summing, well, let's see. it's not even summing across the row, right? Because
Oh yeah, that one.
so actually what it's telling us is it's grouping all of the flights together. So like out of 4,000 some odd flights, 62% of them were American flights that were not delayed by 30 minutes. So if we add up all four, excuse me, of these totals, this adds up to 100%. But that's not really what we want to answer here, right? We'd like to compare American to United. So if you kind of look back over here with this prop table, we can make this into a conditional distribution if we want to sum up either the rows or the columns to equal 1. Right now, we're treating like this as like just one entire sample space of all flights. So in this case, if I want to make sense out of this, I would probably like the sums of my columns to add up to 1, right? Since I would want this to account for these two values here, well, to account for all of the United flights, right? And so if I want to make it so that I can kind of keep track of American down column 1, United down column 2, this is telling me I want sums down each column to equal 1. So I'm going to add this over here, which is going to tell R to do it in that way. And now we're getting things that are adding up to 1 down each column. So this is a way of helping me see that out of all American airline flights, 86% of them were not delayed by 30 minutes. About 14% of them were delayed by over 30 minutes. And here I can see that, relatively speaking, United has a little bit higher percentage of delayed over 30 minutes than American does. So these are some things to be careful about. I mean, R is really good at calculating these things, but it doesn't know what is meaningful to look at. And so that's something that you need to consider first, and then have R do that calculation. And then I think if we bar plot this, what will we get? Then that kind of evens things out a little bit. And now I can see that the light gray area in United is, relatively speaking, a little bit bigger than the light gray area is in American. So all of this is to say that even though R is going to do a lot of this stuff for us, R doesn't know what is relevant and what's not relevant to look at. And so we still need to think about these ideas first on paper, and then we can think about how we can command R to do those calculations for us. But I'll stop at this point, since I don't want to get into filtering or histograms just yet. We can worry about that after the exam. So as far as the exam goes, the only stuff in R that you'll be required to do would be to work with the distributions, using p norm, q norm, all of those types of things. We won't be dealing with bigger data sets on this exam, but that will be the focus for the rest of the semester. And if you want to play around with some of these scripts, I did upload some of them. And they're up in Canvas. Let's see. Wrong class. Here we go. So for example, if you want to play around with these data sets, next time we'll get into this a little bit more. But there's a script called EDA flights. And you can see that when we're working with these scripts, I generally just enter these commands right away, since now this code is going to know I'm going to upload these two packages before I go on to the rest. But this file has a bunch of these commands that we've been talking about, and has some comments in there to explain what each of those commands are. So feel free to play around with that file in the meantime. But Monday we'll have our midterm, and then Wednesday of next week we'll pick up working on the rest of this worksheet. Any questions? So then let me just point out where we can find some stuff. I put up all the exam stuff in Canvas. So in particular, I will go through grading your homeworks that you submitted on Monday. I've been grading them. I'll get those grades done tomorrow. But in the meantime, the solutions are up in Canvas. You don't want to see exam 3 yet. Homework 3. You can find those solutions over here, but in the meantime, I'll be grading them and giving you comments back on them. And the homework that you guys have this week, which is not going to be collected, I did also put solutions for that up just before class, so you can check your work on those as well. Otherwise, here's stuff to help you get ready for the exam. I showed you some of this stuff. You know, if you want to tweak this formula sheet, you're welcome to do that. So during the exam, you're welcome to use any materials that you've created yourself. You're not allowed to use materials that other people created. That means you're not allowed to use my solutions. You're welcome to use your own solutions to homework assignments. And you're not allowed to use internet or work with classmates on the exam. I just want to be sure that that part is clear. So, you know, you guys will be on Zoom just like you are now. Cameras will be turned on, and I'll be here in case, you know, you've got a question about something on the exam. But there'll be 2 parts to it. There'll be a first part, which will be multiple choice, and those questions will be, or at least short answer or multiple choice. So there'll be like reading quiz questions in some sense. And then exam part 2 will be short answer, show your work, more like some homework questions that we've had. And so that part you're going to upload into PDF and submit it up here. So are there any questions that you guys have about the exam?
Is it okay to have notes like on our desktop, or should they be printed out? Can we have them open? Can we have them open on our desktop, or like if we don't want to, you know, save paper and we don't want to print them?
Yeah, I mean, I would say that you just want to be careful, because it's like a double-edged sword in some sense, saying that like you're welcome to use any of your own stuff during the exam, because the intent shouldn't be, and I'm not interpreting your question that way, Christina. So let me just answer your question first, which is yes, you can do that. You can, whether you have them electronically or on paper, that's fine. I'll just say resist the temptation of planning to have like a million documents with you while you're taking the exam, because that's going to take up a lot of time hunting through things to figure out when did we do this problem and how can I do it over there. So I would really encourage you to have like 1 or 2 pages. Anything more than that during the exam, I think, is going to slow you down. So I wouldn't suggest having more than like a notebook page, whether that's on your computer or on a piece of paper. That's for you to decide. Yeah, so you're welcome to use anything that you've created yourself. Whether that's on paper or electronically, that's fine. But yeah, make sure that you've got a lot in here so that you don't need to be like shuffling through like, where is this thing over here? Because that'll slow you down during the exam. So my intention is that you guys have like 1 page of notes that you're using. Of course, I have not really any way of enforcing that, so I won't limit you to that, but that's kind of what my intention is. Yeah, so I would try and encourage you to prepare for this exam the exact same way you would if we were all sitting in a classroom together and I told you you could have one piece of paper with you. What other questions? Either exam or can we do another example like this or whatever? Happy to help you guys. Time is yours.
I think I have a question.
Yeah.
How is if you can answer this, how is the exam going to be weighted with respect to the chapters? Will it be more like from 3 and 4, or will it be earlier material?
Yeah, good question. Let's see. So, yeah, so here's the topics. I mean, as far as like what we just did with central limit theorem type stuff, you know, you wouldn't get as far as like short answer problems, you know, at most you'll have one question that has like use this central limit theorem, kind of like we started class today to calculate how likely is it you pick a sample that has a mean of a certain type. So I wouldn't expect more than a problem on that. Yeah, I mean, I would expect that you'll have to do some work with joint distributions, whether that's continuous. You know, here's a joint distribution, find the marginal distribution for X, find the marginal distribution for Y. So something to be sure that you practice that we haven't been doing in class together, which is doing the integration. Make sure that you're good with the double integrals because, yeah, you very much should expect to say, here's a joint distribution for two continuous random variables, calculate probabilities, find marginal distributions. All of that stuff requires some integration. So yeah, I would say it's going to be pretty evenly balanced between you know, doing some stuff with probabilities, working with commonly used discrete continuous distributions. So I would say, you know, we've done stuff in chapters 1, 2, and 3 and 4. I think it should be pretty evenly weighted in those. So at least one question from each of those chapters. And if you're going to see multiple questions, yeah, I'll say it's more or less going to be equally weighted. Yeah, that's my goal at least.
Okay, thank you.
I am finishing your exam, so that's why I'm a little hesitant to answer, but I'm happy to update you once I finalize the exam. Any other questions? Well, if you do have some questions, I will stick around. If you've got other things to do, go for it. Have a good afternoon. I will be in office hours tomorrow from 10:30 to 11:30. If you do want to go over some questions about homework or getting ready for the exam, I'm happy to help you. Otherwise, good luck. I'll be checking my email over the weekend if you have some questions. And otherwise, I'll see you guys on Zoom on Monday.
Thank you.
Yep, have a good one.
Thanks.
Bye.